So far, we've done 3 examples of training a neural network using TensorFlow. We classified IMDb movie reviews, we classified Reuters newswires, and we predicted housing prices. And in each example, we observed overfitting. Overfitting is the central obstacle that we are faced with in machine learning. If you have a very flexible model, then your model is like a contortion artist, and it will bend over backwards to explain your training data. Your decision boundary, if you're doing a classification problem, your decision boundary might exploit quirks in the training data set, which are not going to be present in the test data set. Your decision boundary will start to do crazy things which are helpful only on the training data set and which will not be helpful on the test data. If your model is overfitting, then the best thing that you can do is get more training data. Another thing you can do is reduce the size of your model. So if it's a neural network, maybe try using fewer layers or fewer nodes per layer. But a third very important thing that you can do is use regularization. And in this video, I'm going to explain what is regularization and how does it work. Before I explain what regularization is, I want to give a general recipe for a machine learning algorithm. So here's a very general pattern that contains many specific examples of machine learning algorithms. We're given some training data consisting of a list of feature vectors, x1 through xn. Each feature vector is a vector in Rd, so each feature vector has d components. We're also given corresponding target values. If we're doing regression, for example, predicting housing prices, then each of these targets, yi, is going to be a number, a real number. If we're doing binary classification, then each target value is going to be a label, either 0 or 1, typically either 0 or 1. And if we're doing multi-class classification, then each target value will be a vector in Rk, where k is the number of classes in our classification problem. And our goal in machine learning is to find a function f, which depends on a vector of parameters beta, such that our predicted value, f sub beta of xi, agrees with the ground truth target value, y sub I, for all of the examples in our training data set. That's our goal. How do we select this vector of parameters beta? What we do is we solve this optimization problem. This loss function L measures the agreement between the ground truth target yi and our predicted target value f sub beta of xi. If this loss is small, then that means the agreement is good. And what we hope is that when we compute this loss for each example in the training data set, and then when we sum up all of those loss values, we hope that the entire sum is small. That means we've done a good job of making predictions on all of our training data. So we choose the vector beta to minimize this cost function, L of beta. And here are some specific examples. In linear regression, f sub beta of xi is given by this formula. These numbers xi1 through xid are the components of the vector xi, and these numbers beta naught, beta 1 through beta d, these are the components of the vector beta. And the loss function that we use is just this quadratic loss function. If we're doing logistic regression for binary classification, then f sub beta of xi is given by this formula. Here sigma is the sigmoid function, also called the logistic function. And in this case, we use the binary cross-entropy loss function to measure the agreement between the ground truth probability, which is either 0 or 1, and our predicted probability. If we're doing deep learning, then we follow the same formula, the same recipe, but now f sub beta is a neural network. Other machine learning algorithms follow the same recipe. For example, f sub beta could be a decision tree. When we train a decision tree, we're using the same recipe. Now we're ready to introduce the idea of regularization. We mentioned that overfitting happens when your model is too flexible, and regularization is one strategy for addressing that problem. The idea behind regularization is to add an additional term to your cost function when you're training your model. And what this extra term does, this is called a regularization term. This term is penalizing us if the vector beta is too large. If beta has a large norm, then we are going to be penalized. This means that we are more restricted in our choice of beta. We can't just choose any crazy value of beta that we want. We have to choose a value of beta that's small. We have effectively reduced the space of allowable parameter vectors that we are allowed to explore because we feel pressured to keep beta small. If we're doing a classification problem and you look at a case of overfitting where you have a crazy decision boundary that is doing crazy things to satisfy the quirks of the special quirks of the training data set, usually that boundary corresponds to a large value of beta. And a smaller value of beta would give you a more reasonable, less complex decision boundary, and that guards against overfitting. So regularization effectively reduces the flexibility of our model, which tends to prevent overfitting. This is not the only possible regularization term that we could use, although it is one of the most popular regularization terms. Here's the general pattern. We train our model by solving this optimization problem. This term encourages us to do a good job of explaining the training data. And this term encourages us to choose a parameter vector beta, which is not too complex. That prevents overfitting. And I mentioned that this regularization term is one of the most popular and most fundamental regularization terms. This is called L2 regularization because the L2 norm appears here. Another popular choice is L1 norm regularization, which is shown here. This is another popular choice for the regularization term. It turns out that this regularization term, where we penalize the L1 norm of beta, has the effect of encouraging most of the components of beta to be zero, so that only a small number of the components of beta are active. And those small number of active components of beta correspond to the most important or the most useful features in our training data set. Next, I want to explain in detail how to do linear regression with L2 regularization. And first, I want to just review standard linear regression, just basic linear regression. We're given a list of feature vectors in RD and corresponding target values, which are real numbers. That's our training data. And here's our objective function. We hope that our predicted value agrees with the ground truth target value for each of the training examples in our training data set. And in matrix notation, this objective function can be written like this. L of beta is equal to 1/2 times the norm of x times beta minus y squared, where x is this matrix here, and y is this vector here. So y contains all the target values, and x is this matrix. To do linear regression with L2 regularization, we just add this regularization term to our objective function. This parameter lambda controls the amount of regularization. So if lambda is large, then our regularization term is very strong. If lambda is small, then our regularization term is very mild and doesn't have much effect. Now, how do we minimize L of beta? Usually in machine learning, we have to use gradient descent or stochastic gradient descent or some optimization algorithm like that. In this case, our cost function is simple enough that we can just set the gradient equal to 0 and just solve for beta. So let's compute the gradient of L. The gradient of this first term, as we know, is x transpose times x beta minus y. And the gradient of the second term, as we also know, is lambda times beta. So this is the gradient of L. Now let's just set the gradient of L equal to 0 and solve for beta. We can rewrite this as x transpose x plus lambda I times beta is equal to x transpose times y. Here I denotes the identity matrix. So this x transpose x term came from here, and this lambda I term came from here. Lambda I times beta, that's the same thing as lambda times beta. And this x transpose y over here came from doing x transpose times minus y. And then we bring that over to the other side and we get x transpose times y. Now this is a linear system of equations, and we can solve this using any method that we like to solve linear systems of equations. For example, Gaussian elimination would be the most common method. So that's how we solve for beta. Next, I want to look at polynomial curve fitting, which will give us a very tangible demonstration of the effect of regularization. So the setup is we're given a bunch of points in the plane, and we just want to fit a polynomial to these points. So our goal is to find a polynomial function, and these coefficients beta naught, beta 1, dot, 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 beta d, those are going to be the coefficients of our polynomial function. Here we have x to the first power, x squared, dot, 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 x to the power of d. This number x, this x is a number that's being plugged into this polynomial function. Our goal is to choose these coefficients of our polynomial so that when we plug the number xi into our polynomial function, the output is a good approximation to yi. We just want to fit a curve to our data. We want to fit a polynomial function to our data. Here's the cost function that we're going to use to select these coefficients, beta naught, beta 1 through beta d. How do we select those coefficients? We choose those coefficients to minimize this cost function. And what this cost function is saying is that we want this predicted value to agree closely with the target value. In other words, when we take xi, when we take the number xi, and when we plug it in to our polynomial function, the resulting value should agree closely with yi. We just want to fit a curve to our data, that's all. This objective function can be written using matrix notation like this, where x is this matrix. So the first row contains the numbers 1, x1 squared, dot, 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 x1 to the dth power. The final row contains the numbers 1, xn squared, dot, 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 xn to the dth power. The total number of rows of this matrix is n. And this vector y just contains all the y values, y1 through yn. So this is our objective function written using matrix notation. We want to choose the coefficients beta naught, beta 1, dot, 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 beta d to make this objective function as small as possible. That means that our polynomial is doing a good job of fitting the data. We can also use regularization when we do polynomial curve fitting. And the way that works is we just take our same cost function and we just add a regularization term. And this is our new cost function. So now we're going to select beta, our parameter vector beta, so that this cost function is minimized. And how do we minimize L of beta with respect to beta? Well, we just set the gradient equal to 0. We don't have to use stochastic gradient descent because this cost function is pretty simple. We can just set the gradient equal to 0. And the gradient of L, as we mentioned previously when we were discussing linear regression with L2 regularization, the gradient of L is x transpose x beta minus y plus lambda times beta. We set the gradient equal to 0, and we solve for beta, and this is the equation we get. This is a linear system of equations, and we just solve it using Gaussian elimination or whatever method we prefer to solve a linear system of equations. So let's try implementing this polynomial curve fitting. Here's some code that generates some data for us. So we're importing NumPy, importing Matplotlib. We're randomly generating some x values, and we're randomly generating some corresponding y values. Let's take a look at the data that we have right now. Let's plot x vals, comma, y vals. Let's see what the data looks like. Okay, so that is some randomly generated data, and you can see that it roughly it looks like it roughly follows a quadratic function. Now, let's fit a curve to the data. So we're going to set d equal, let's try d equals 2. D is going to be the degree of our polynomial. Let's try a second degree polynomial first. So what do we need to do? We need to construct our matrix X. Remember that our goal is going to be, we're going to solve X transpose X equals X transpose Y. And that if we're not using regularization, then this is the system, the linear system of equations that we're going to solve in order to get our polynomial coefficients. So in order to implement this, we need to construct the matrix X. So let's do X equals np dot zeros of n comma d plus 1. And then let's have a for loop that just fills in the values of this matrix X. So for I in range of n, and then we'll do for j in range of d plus 1, and we'll say x of ij is equal to x vals of I to the power of j. And now we've just constructed our matrix X. Let's take a look at this. I'll just print out X. There it is. That's the matrix X. Okay. Now let's compute, I'll call it xtx. It's going to be equal to the transpose of X multiplied by X. And let's also compute, I'll call it xty. It's going to be equal to the transpose of X multiplied by y vals. Remember, this @ sign is how you can do matrix multiplication in NumPy. Now we need to solve this system of equations, and NumPy will solve that system of equations for us. Let's do beta equals np.linalg.solve of xtx comma xty. And this handy solve function just solves our linear system of equations for us. If we looked under the hood, it would be doing probably Gaussian elimination. Okay. Now let's make so we've got beta. Let's run this section of code, and let's print out beta. There we go. And now let's see how well our polynomial fits the data. So let's do y predicted. This is like our predicted values of y. To get our predicted values of y, we can just take x and multiply by beta, and that gives us our predicted values of y. Okay, now let's plot the data, and let's also look at our predicted y values. Let's see how well we've done at fitting the data. So I'll plot x vals, comma, y pred. Okay, let's run this. Okay, so that's a nice fit. We used a degree 2 polynomial, and we got a nice fit to the data. But what would have happened if we had used a higher degree polynomial? Let's use a degree 9 polynomial. Now, instead of 3 coefficients, which is the number of coefficients we had with our quadratic polynomial, now we have 10 coefficients. That's the number of coefficients in a degree 9 polynomial. So we are now using a much more flexible model. And let's see what happens. Okay, so you can see that this model is overfitting. It's trying to satisfy, it's sort of bending over backwards to satisfy the training data. What it's doing here is helpful on the training data, but this is not going to be helpful in the future when we're given new data that our model has never seen before. This is our model overfitting. So to prevent this overfitting while still using a degree 9 polynomial, let's try adding L2 regularization to our objective function. Let's use a value of lambda that's equal to 100. And remember, the system of equations that we have to solve in order to minimize our objective function when we're using L2 regularization, the system of equations is x transpose x plus lambda times I times beta equals x transpose y. This is if you remember, this is the system of equations that we need to solve. This came from setting the gradient of the objective function equal to 0. So let's construct this matrix, x transpose x plus lambda I. So we'll do matrix equals xtx, which I've already created, plus lambda times, and I'll do np dot identity of d plus 1. That creates, this NumPy function creates an identity matrix. So let's just take a look at what matrix is. There it is, its shape. Matrix is it's a 10 by 10 matrix, okay. And now now we're ready to just solve our system of equations. So let's do beta reg equals np.linalg.solve of xtx, solve of matrix, and then the right-hand side of our system of equations is still xty. So that's beta, that's the coefficient vector that we get when we're using L2 regularization. So let's look at how well our model fits the data now. So let's do x times beta reg, and then let's plot the data, and let's plot the polynomial that we got without using regularization, and let's also plot the result that we get using regularization. So here, instead of y pred, I'm going to have y pred reg, and let me make this polynomial curve appear as a dashed line. Okay, we're ready to look at the result. Okay, that's what we got. This curve in green, that's the polynomial fit that we get using regularization. So this green curve, we're still looking at a degree 9 polynomial here, but notice it's not overfitting the data anymore. It's doing much better because of the regularization. So that's a very tangible example of how L2 regularization can prevent overfitting.